Right, in this video we're going to finish up section 2.3, linear functions and slope. And we're going to start this video with the good old slope-intercept form of the equation of a line. So the slope-intercept form of the equation of a non-vertical line with slope m and y-intercept b is y equals mx plus b. And they call this slope-intercept because when you have it solved in this form, y equals whatever's in front of the x is your slope, and whatever this number is, sign included, is your y-intercept. So we have seen that functions in this form are called linear functions. Thus, in the equation of a linear function, the coefficient of x is the line slope, and the constant term is the y-intercept. And here's two examples. When you see y equals 2x minus 4, you immediately know the slope is 2, and the y-intercept is negative 4. Here's another one, y equals a half x plus 2. Again, the number in front of the x is your slope, so our slope is 1/2, rise 1, run 2, and the y-intercept is positive 2. If a linear function's equation is in slope-intercept form, we can use the y-intercept and the slope to obtain its graph. And the steps to do that, step 1, plot the point containing the y-intercept on the y-axis. Just do a quick generic representation. You're going to find your y-intercept somewhere along the y-axis. Maybe it's positive up here and maybe negative down here. Obtain a second point using the slope m. Write m as a fraction and use the rise over run starting at the point containing the y-intercept. That is the number one mistake I see a lot of students make here. Like, let's say we found the y-intercept is right here and the slope is a half. It is a common mistake to come back to the origin and do the rise 1 and the run 2 from the origin. The reason we do the y-intercept first is that's our starting point. So find the y-intercept, and from that point we would do the rise and the run. Here it'd be rise 1, run 2, 1, 2. There's our second point, and then we can draw our non-vertical line. So once you get the second point, you can use a straight edge or a ruler to draw a line through the 2 points. Draw arrowheads at the end to show that the line continues indefinitely in both directions. So here they gave us an equation. It's ready to rock and roll. It's in the form y equals mx plus b. Again, don't let the f of x throw you. You know, f of x is just a function notation for the output of our function, which we can also use y for. So this would be y equals negative 3/2 x plus 2. So notice too, I put the negative distinctly in the numerator because when it's just with your numerator, positive rise is up, negative rise would go down, and that way the run is always positive, so you always run to the right. So our y-intercept, positive 2, I'm going to put a dot there. Our, again, slope is negative 3/2. Because it's a negative 3, from the y-intercept I'm going to go down 3 units, and then I'm going to run 2 to the right. So here's my second point. And since we have 2 points, we can connect the dots and draw arrowheads on each end. And I hope my graph matches the book's graph. And there we go. Y-intercept positive 2, rise down 3, over 2 for the run. Now, if we have the equation of a horizontal line, it's just going to be in the form of y equals some number. If you really want to see a slope in there, you could always write y equals 0x minus 4. And to make your slope look more like a fraction, like rise over run, we can always put a 1 under that numerator. So here it might be easier to see this does tie in nicely with slope-intercept form. Y-intercept down at negative 4. And then our slope is 0 over 1, or rise none, run 1. So we're not going to go up at all and just run 1, run 1, run 1. Connect the dots, and we have our horizontal line. It's easier to think when you see y equals a number like negative 4. You know that's the axis that you touch, the y-axis, at the point negative 4. And that's the only time you touch the x or the y-axis. So we are going to have to be parallel to the x-axis, which makes our line horizontal. If we have a vertical line, that's going to be given in the form of just x equals some number. So that's the only place we're going to cross an axis, and we're going to cross the x-axis at that point. And since we're never going to cross the y-axis, we're going to be parallel to it, or our line will be vertical. So here's our example, x equals positive 2. Follow the x-axis to positive 2, put a dot there. That is the only place you cross any axis, so we can draw our vertical line. There's another form of writing the equation of a line. It's not quite as useful as slope-intercept, but it's called the general form. and that we just have our x variable first, plus or minus some number times our y, plus or minus our constant, and the whole thing is set equal to 0. A, B, and C are real numbers, and A and B are both not equal to 0. So in example 7, find the slope in the y-intercept of this line. I'm just going to copy it here. 3x plus 2y minus 4 equals 0. Well, when it says find the slope in the y-intercept, the easiest way to do that is put it into slope-intercept form. So we're going to solve to get y alone. So the first thing I want to do is add 4 to each side and subtract a 3x. So I'm going to subtract 3x from the right, and I'm going to add 4. And last step, divide by 2, and don't forget to divide every term by 2. So now we have y equals negative 3 halves x plus 4 divided by 2 is 2. Well, they asked us to find the slope, and the slope is right here. It's negative 3 halves. And they asked us to also find the y-intercept, and there's the y-intercept, positive 2. Put it in slope-intercept form, and those two things jump right out at you. All right, we can use also another method to graph a function is to find the intercepts, and that's just where we cross the x and the y-axis. So to find the x-intercepts, we let y equal 0 and solve for x. To find the y-intercept, we let x equal 0 and solve for y. And that way we'll have a point on each axis, and once we have a point on each axis, we got 2 points, and we can connect the dots and draw our straight line. So when I'm doing this method, I like to get my variables on the left, and I'm just going to get this number on the other side. So I'm going to add 6 to both sides. So now I have this, 4x minus 3y equals 6. Well, the first thing we can do is let x equal 0, and if x equals 0, I can just cover this part up. And now I have minus 3y equals 6. So minus 3y equals 6 will give me one of my intercepts. Divide both sides by negative 3, and I get y equals negative 2. I can put a dot on my y-axis at negative 2. Okay, so the first thing we did was set x equal to 0 and solve for y. Now we're going to set y equal to 0, and that's just like covering this up. The 0 for the y will wipe out that whole term, and now we have 4x equals 6. Divide by 4. X is 6/4, or 3 halves, or if you like decimals, 1.5. So we're going to go on the x-axis to 1.5, and now we have 2 dots, one on each axis, and we can connect the dots and draw our line. So that's the intercept method. Give each variable a turn equaling 0, and find where you cross the x and the y axes. So now we've covered quite a bit of territory. Let's stop back and take a look at a summary of all the various equations of lines. Point-slope equation, very handy if they give you a point and the slope of the line. Slope-intercept form is very good to find the slope and the y-intercept of a line. Very easy to graph in that one. Horizontal lines are just y equals a number. Vertical lines are x equals a number. And then we have our general form. X plus or minus b plus or minus a constant, all set equal to 0. Remember, general form, you set it all equal to 0. All right, here's some practice problems for your fun. Number 4 is just like the first example. Graph 5 and 6 you can do on the same axis. Graph those vertical and horizontal lines. And then there's one to do by the intercepts and one to put into slope-intercept form, and then graph. Alrighty, so pause the video, try those out, and then see if you got them right. All right, first one was handed to us, ready to rock and roll. Y-intercept positive 1. Slope is 3/5, or up 3 over 5. So up 3 and then over 5 would take us right to here. If for some reason that would take you off the graph, you know, we went up 3 and to the right 5, you could also negate both of them, and now it would be down 3 and to the left 5. And if we do that, we see they all do line up nicely, and we can draw our arrows. There's our line. All right, down on this one, we're going to graph these both on the same axis. Y equals 3 just means we cross the y-axis at 3, and that's the only axis we touch anywhere. So we have a horizontal line. And then x equals negative 3 is x-axis to negative 3, and that's the only axis we touch anywhere. So we have a vertical line going through that point. Checkpoint 7. Find the slope and the y-intercept of this equation. and then graph it. So we have 3x plus 6y minus 12 equals 0. Easiest way to graph is to put it in slope-intercept. So I'm going to subtract 3 and add 12 from each side. So subtract 3 and add 12 on the right, and that's equal to 6y. And now, of course, divide by 6. Each term gets divided by 6. So we have y equals negative 3 over 6 reduces to negative a half x. 12 divided by 6 is 2. So our y-intercept is 2. Put a dot there. Slope is negative 1 and then run 2. So we go down 1, run 2, down 1, run 2. Connect the dots. Negative slope, lines going downhill. So here we have one that says graph using intercepts. First I can cover up my x coordinate, and then I see I have, well, let me get that 6 out of there first. I'm going to add 6 to both sides. So now it's equal to positive 6. And if I cover up my x, I see minus 2y equals 6. And I'll switch over to blue for the other one. And if I cover up my y coordinate, I see 3x equals 6. So here I would divide by 3 and get x is 2. X is 2. And here I would divide by negative 2 and get y equals negative 3. So I can put my y-intercept at negative 3 and then connect the dots. All right, good times. Speaking of good times, here's some homework for your mathematical pleasure tonight. Pay special attention to the even problems. Again, they're not in the back of the book, but they're very similar to the adjacent odd problems. I'll see you in section 2.4.